This exaggerated contrast at the edge of a stimulus is known as edge enhancement. This phenomenon helps us perceive where one stimulus ends and another begins, but it can also produce an optical illusion known as the Mach band illusion. Each of these vertical strips visible in the figure is made up of a uniform color, but the strips do not appear to be internally uniform. Instead, they appear as a gradient of brightness, each brighter on the left and darker on the right. This results from the contrast on the left-hand side to a darker strip, making that area appear brightest, and a lighter strip on the right, making that area appear dark. We can see that they are illusions if we block the boundary line between the strips, like this. Now it's easier to see that the colors are indeed uniform. But as we remove these matchsticks blocking the border, the illusory gradient returns. Of course, that illusion disappears again if we block the border again. Because this occurs during the process of receiving stimulation, which is why this is called bottom-up processing, it is impossible to prevent this illusion from occurring or to change the perception of the gradient without blocking the edge between the strips that differ only in their brightness. A Necker cube is a type of figure that is ambiguous or reversible. It has only one set of visible features, the lines and the negative space between them. However, it is a set of features with multiple available interpretations. It can be perceived as though from above, like this, or it can be perceived as though from below, like this. Despite this ambiguity, it can only be perceived in one of these ways at a time. Go ahead and try and see both of those at once. You can never quite maintain both perceptions at the same time. The features of the object are totally neutral because the drawing is compatible with either interpretation. So the way that you perceive it includes a specification of depth arrangement, assigning some of the features to the front of the cube and some to the back. So these perceptions are not simply bottom up, but rather are also a function of prior knowledge of the possible orientations and an executive decision as to which orientation to apply in your visual perception of the object's features. This type of recursive parallel processing happens in other ways with other stimuli as well. Some figures are neutral with regard to figure-ground organization. That is to say, which parts of the stimulus is the background and which part comprises the foreground or figure upon that background. In this figure, two interpretations are possible, each based on a different figure-ground organization. Are the black faces in the foreground against a light-colored wall or sky? Or is this a white vase against a black background? The same is the case for this flag. Is it a red flag featuring a white foreground square showing two arguing faces with prominent brow ridges and long sharp noses, each wearing a high collar and having square shoulders? Or is it a white flag with red stripes and a red maple leaf laid over the background? Again, in both cases, the gestalt, or the whole perception of the image, contains additional information that is not supplied by the stimulus itself. Thus, the idea that prior knowledge, including your hobbies, preferences, education, and many other things, contribute to the way you construct perceptions seems inescapable. Your role in shaping your own experience with the world seems undeniable. But ambiguous stimuli like this can be argued to be specially constructed to bring out these ways of perception, to facilitate flip-flopping between one perspective or another. It does seem conceivable that we may play less of a role in the perception of objects than occur more naturally in the world. Objective reality is not the purview of art, after all. The path of a car down the street, the level of a beverage in a glass, the letters in our mailbox, or the shape of the face of our romantic partner. These are objective realities that we all share without personal influence on the perception, right? No. Most stimuli require interpretation and are thus ambiguous. What about this? It doesn't seem ambiguous, but let's think about it carefully. This annotated outline will help. Didn't you perceive that shapes B and E were different parts of the same apple? Not different objects, but differentially visible portions of the same object, simply hidden by D, the banana. Further, there appear to be other red objects, the grapes, A, and the tomato, right below them. They're all touching and they're all red, but they are different objects, right? Does the blue object in the background continue down, or is it part of the bowl? How do you know that the blue and green stripes continue beyond that blue item that looks like a pitcher? The stimulus itself tells you none of this. Instead, you're relying on prior knowledge generated from previous perceptual experiences with similar objects in similar environments. We do this all the time. Look around the room at all of the partially hidden objects. You know that they have continuity, but you can't see it directly. This unity of form and the continuity of objects is entirely in the eye of the beholder, though it never feels like an active interpretation. Thus, interpretation can often occur before information gathering. Let's take a look. Here, the figure often appears to be odd black shapes, at least at first glance, without the shapes necessary to form letters or a word. But once we reorganize an initial perception that the white is the background, and try thinking of the black as the background, the letters appear, and then so does the word. What this shows is that the perception or the meaning derived from the collection of features depends on how your mind is organizing the elements of the figure. With this figure, I'm sure that by the time I finish the sentence, you'll have perceived it as being a word. You probably never detected yourself seeing it as a strange collection of thin, curved, or zigzagging black lines. But many of the necessary features to make this word are not present, though most people supply them readily. Such manipulations can cause visual illusions. Let's see two examples. These tabletops appear to differ by both shape and by size. However, this contrast is an illusion, and the tabletops are actually identical in shape and size. The illusion is caused by the same mechanisms that, in most circumstances, allow you to achieve constancy. Cues to depth in this figure cause you to perceive the figure as a drawing of three-dimensional objects, each viewed from a particular angle. This leads you, quite automatically, to adjust for the apparent viewing angles in order to perceive the two tabletops, and it's this adjustment that causes the illusion. Shape constancy works against our accurate perception in this case. Let's look at another. Again, these monsters look to be quite different sizes, but let's pull them out of their tunnel and compare them. Again, this is an illusion, this time created by the distance cues, height combined with perspective, the convergence of the tunnel lines in the distance, and the relative sizes of the bricks in the tunnel. In this illusion, size constancy is what's working against us. I'll put them back in opposite spots and we'll see again that their apparent sizes are an illusion. The one from the foreground now looks larger and vice versa. The last illusion we'll look at takes us back to the last type of cues we've discussed relating to constancy, brightness cues. Take a look at the central square, third row, third column. It appears much brighter than the square marked by an arrow. Once again, though, this is an illusion. Let's take a look. See, the color of the central square hasn't changed, but it's clear that the two squares have the same color. Let's bring part of the board back again for context. Now the full board. Here, lateral inhibition produces a contrast effect. The central square in this figure is surrounded by dark squares, and the contrast makes the central square look brighter. The square marked at the edge of the checkerboard, however, is surrounded by white squares. Here, contrast makes the marked square look darker. The shadow cast by the cylinder amplifies the effect. And you therefore make an unconscious inference that the center square is brighter than the marked square at the edge or any of the dark but unshadowed squares on the board. Unconscious inferences of this nature are central to our perceptual system. The chapter discusses a few more that we're not going to cover here, including the role of education and experience in perception. Next time, we'll discuss how we take these types of inferences and use them to label or recognize whole objects.